So the next talk, if there is no more questions, would be by Nurit Shtober Zisu and Leah Wittenberg. So they are both from Israel. And Nurit is from the Department of Israel Studies, and Leah is from the Department of Geography and Environmental Studies, and they are both from the University of Haifa. And they will present us long-term effects of wildfire on rock weathering and rock stoniness in the Mediterranean landscapes. Well, so that's your turn, Nurit and Leah.
Thank you very much. Do you hear me?
Yes, that's fine.
And where is the, okay, this is it. So hello,
Okay, that's
evening.
fine.
Thank you, Monique. Thank you, everybody. Good evening. Here it's 6 o'clock in the evening already. And good evening, everybody. I'm Nurit Shtober from the University of Haifa. And together with my colleague, Leah Wittenberg, we would like to present the long-term effects of wildfire on rock weathering and soil stoniness in the Mediterranean landscapes. It's a research that we conducted during the last year, but it started way back 10 years ago when a major wildfire hit Mount Carmel. Mount Carmel is a mountain in northern Israel. I live on Mount Carmel. Haifa, my city, is there. And this is the view from my home in 2010. That's the ash cloud above my home, above the Mediterranean. I live by the coast. And that's Kibbutz Beit Oren, that those houses were evacuated and later on completely burned. So a deadly forest fire in Mount Carmel consumed approximately 2,500 hectares of forest and Mediterranean chaparral in those 5 days. It was the deadliest and the costliest forest fire in Israel history. That's the map of the fire severity that was completed later on. As you can see, the red color represents the high severity areas. We don't know about the ground temperatures, but we do know the vegetation, the large trees and the coniferous trees and dense and mature coniferous trees. They created a very high or high severity fire. As you can see here, everything is red. The next day after the fire was extinguished, we were in the field, well, 2 days later. And in terms of rocks, this is what we saw. Rocks suffered from or underwent thermal shock and massive destruction. Up to 100% of the rock surface was affected, was destructed. Here you can see 100% of the surface, and here you can see the onion skin-like structure of flakes, one atop the other, that fractured the rock up to a depth of 10 to 20 centimeters. Most flakes and spouts were in forms of shapes and blades like this one. They were thinner and elongated. And that was the picture in 2010. This is what we saw in 2010. So to express these photos in values, okay, so Mount Carmel is composed from carbonate rocks, mostly chalk, limestone, and dolomite. Now, these graphs show the orange colors represent the chalk, the grayish or greenish or whatever color represent the limestone, and the darker brown represent the dolomite. So as you can see, if we look at the percentage of spout surface by formation, we looked at the geological formations. The chalks were the most affected rocks. In terms of percentage of spaled surface, in terms of maximum thickness of the spaled surface, as you can see, one chalk outcrop lost in one particular fire 8 to 10 centimeters of its surface. It's a lot. And of course, the average size of spalls distributed by formation. Again, the names are not significant, but yeah, look at the colors that represent chalk, limestone, and dolomite. So the chalk were the biggest and the most affected rock, and that probably the thermal shock affected, or the petrophysical properties of the rocks, like the hardness, the porosity, the density. They reacted with the surface, and this is what happened. But that was the introduction. That was 2010. Now let's look what happened. What happened 10 years later. These are the same outcrops, 2010, 2020. You can see what happened to them. Those flakes that apparently exfoliated and exploded within the rocks are gone. So these photos in our field campaigns triggered the next questions. Where are these flakes? What happened to them? Where are they? And are they within the soil? Have they been transported down slopes? Where are they? So that brought us to the two aims of the study: to monitor and analyze the long-term 10 years change in the burned rock surface, and to monitor and analyze the properties and the distribution of the fire-induced flakes. Again, Mount Carmel and the burned area in black. Mount Carmel, this is the Gulf of Haifa, the Haifa Bay, the Mediterranean coast. Mount Carmel is about 230 kilometers, square kilometers. It's composed mainly of marine carbonate rocks from the Tethys succession. And we can talk about five lithological units that were mostly affected by this fire. Again, the names are not very important, but okay, Yagur formation is dolomite, and then we have chalk, and another one, Arkan, is chalk, Mokwaka is limestone, Sumac is chalk. So we have one limestone, one dolomite, and three affected chalks that we're going to talk about them during that talk. Method, what we did. So we tested rocks and we tested soils. We tested the rock surface using the Schmidt hammer. The Schmidt hammer is a device that tests strength. It measures the elastic rebound of the surface. That obviously depends on the hardness of the rock. And then the values can be converted into compressive strength. And we measured soils. Measured 75 microplots. They were documented and sampled across those 5 geological formations. 15 samples were taken from each formation, 10 from burned locations, and 5 controls. And a total of 50 microplots were previously sampled in 2010 and published. And then we went back to see what happened to the 2010. We compared the fragments measured in the same formation and location in 2010. We collected all the rock fragments from the surface, wet sieving and removing the small particles, and then were dried. The remaining soil was dried, and we collected the gravel, and measured the pebbles, which were larger than 16 millimeters in diameter. And the results were compared with fragment measured in 2010. Let's look at the results. In terms of rocks, what we see here is the elastic rebound measured using the Schmidt hammer over flake surface in 2010. 2010 are the gray colors. The darker color is the average value. So these are the values in gray colors. Again, for the chalk formations, limestone and dolomite, 5 graphs for 5 units. Gray is the 2010 values. Pinkish or orange, it's the 2020, and the green ones are the control values in areas that were not burned for at least 80 years. As you can see here is that the test revealed high variability between the exposed lithologies, as well as between the data from 2010 and 2020 and controls, and the measurements of the outcrops that were burned in 2010 were, the 2010, as you can see here in 2020, the values are very much similar to the control areas, which means that in 10 years, the flakes are gone and the surface is almost completely back to normal, back to control or back to unburned. That's about the rock. Now about the soil. Soil stoniness is defined as the percentage of the rocks in soil. It can be measured on the surface and it can be measured within the profile. In the present study, we measured the rock surface. We collected the surface. From a simple photo, you can see, okay, so these are the dolomite, one burned 2010 control, dolomite burned 2010 control, chalk, burned 2010, and control. You can see that the surface, the soil surface, was the most affected in the study area. Now that's the surface. Let's look at the weight. Surface stoniness by weight. Of course, the same picture. We can see the burned chalk. The burned chalk was the most affected, and 10 years after the fire, the volume of the stoniness in the chalk is the higher. Now, the cumulative curve of the rock fragment weight distributed by size. The median in all burned chalk is 8 to 16 millimeters. In the category is 8 to 16. And we can see that after the fire, or in the unburned area, the median values in the unburned chalk is 2 to 4 millimeters, indicating the tendency of the porous chalk to break down, to pulverize, and to be transported down the slope. As for the shape, here you can see the gray dots. The gray dots represent the 2010, and the tiny triangles represent the 2020. That's the zinc diagram. The zinc diagram refers to the axis of the particle, and when we measure the axis, the A, B, and C axes, we can transform them into a graph, and we can relate their specific shape. So they can be equant or prolate or oblate or bladed. Now, if we look in 2010, most of the shapes were very flat. They were dislocated from their surface, and they became spalls and flakes. Now, in 10 years, they broke down and became much more equant and prolate. And if we look at to what degree or what extent, basically this graph is more or less like the previous one. The more means the more prolate and equant. So we can see for each and every rock formation, but mostly for the chalk formations, we can see a tendency toward more breakdown and more sphericity of the particles. Of course, they broke down. To summarize the model of change in stoniness, or what happened there, we'll start before the fire. If we start before the fire, we see the shrubs and trees and the rock surface and everything is normal. Then the fire reset the area and everything is covered in ash. The rock surface is burned and spalled. In 3 years, we started to see the dislocation and the transport downslope of these spalls and flakes. And in 10 years, the new rock surface is exposed to the atmosphere and new weathering. And this image always reminds me that after a forest fire, everything comes back vegetation and the butterflies, the ants, the biological factors. Even the soil is back in several thousand years. The only factor that never comes back is the rock surface. Now, if we look at the soil, or what happened to the stoniness in soil, we can see that, previous studies show that immediately after the fire, the fine-grained particles are removed by either wind or overland flow, and the residual fine sediments quickly becomes protected by either re-exposure of a stone armor layer, like here, from a previous event, or by the new layer of the eroded rock. Here, it's visible in the second. Now, also previous studies suggested that increasing rock fragments cover is usually associated with the removal of fine soil particles and the roughness of the surface increased. But in this present study, we show that the rock surface stoniness in the vicinity of the burnt chalk 10 years after the fire is 2 to 3 times greater than the stoniness in the control sites. I think this is the end, more or less. So we see the increasing stoniness. And to conclude, do I still have time to conclude and to read the conclusions? What time is it? Yes, I do. So when exposed to high temperatures, rock tends to disintegrate and exfoliate. Chalk exposures are more susceptible to the effect of fires than hard dolomites and limestone. Within a decade, the exfoliation was nearly completed. Flakes and spalls are almost completely detached from the rock outcrop and exposed fresh rock face to the with hardness similar to the control unburned rock. The formerly detached spalls and flakes underwent pulverization and formed small fragments enriching the soil structure. And of course, the most affected soil is the Rinzino soil, which covers the chalk of the Sphia Formation, one of the chalks. The fire-affected chalks were severely weathered and produced large and abundant gravel, and the magnitude of the impacts of the limestone and dolomite is milder. Those results have implications for post-fire erosion modeling and soil conservation in areas with the same climate and rock characteristics, but further research, of course, is needed. We summarize this work in this year in a paper we published, and in the Science of the Total Environment. And to conclude, well, to say a big thank you to Hilit Cranenbrook from the University of Haifa for her valuable contribution to the field and lab work. Hilit is in the left and Leah and I on the right. And Hilit has established a new term in geomorphology. She texted me before, Happy Geomorpho Ladies Day. So with this, I will say thank you, everybody, and that's it.
Well, thank you very much. Thank you very much, Nurit, for this very, very nice presentation. Very interesting. And your last point in your conclusion was to mention, is there any other studies on different type of parent material? And I remember I was still a student, so it's a long time ago. I was in the southern part of France, in the southern Massif Central Massif of France, on the Mediterranean side, and there was evidence of recent fire, and they were gneissic material, and we observe exactly what you described. So, of course, maybe the flaking was not as much developed, but I remember it was quite impressive, you know, of that. So that's an idea of, you know, having different sites that you could expand your study. So Well, now this is open to questions. No questions? Well, Nurit, it seems that you didn't have the opportunity to start again this type of research. Does it mean that your country is not affected by any more fires?
Oh, well, yes, it is. And Leah, will you please help me, because this question is right for you about fires in Israel?
Yes, there was a very large fire last year, not far away from Jerusalem in the Judean mountains. But this specific research we are following with several studies. We keep following the events of 2010. So we are actually, it's kind of strange to say, but we are very lucky to have this opportunity to follow long-term effects of wildfire. But nonetheless, we have almost every year, we have a new fire if we'd like to establish a new research campaign.
Yeah. Well, I'm not wishing it for you and for your country, you know, but it's a problem, and especially, you know, I think that the last year we have seen many fires in in different parts of the world, and it would be interesting to know whether the scientists have locally started such studies like yours, which is really interesting.
We have a cost action. It's a European endeavor. We have a cost action called the Fire Links.
Yes.
So I can share the details, and people that are interested in wildfires in Europe can join this action. I will
put
the link in the chat.
Yeah.
So it is an ongoing action, and actually we meet every couple of, now with the COVID-19 we meet online, but we have several meetings actually every month almost to discuss wildfires basically in Europe, but we have also colleagues from Australia and from the US that collaborate with us on these topics.
In California, I think that the past year was really terrible. Huh?
Mm-hmm.
Yeah.
And also Australia as well.